So, welcome to the next lecture, instruction format and addressing modes. So, what do you mean by instruction format? So, we know what is an instruction, and instruction format is what it comprises of two parts. First part is the opcode and the next part is the operand. So, what is an opcode? So, if we take an example, let us say add R1 R2. Opcode specifies the operation to be performed. That means, here what operation is to be performed? The operation here is adding two register values, and these two register values will be added and stored back in some register. This instruction specifies. So, R1 will store R1 plus R2. Add is the operation code that specifies the operation to be performed by the instruction, and we can have various categories of instruction. So, this is an arithmetic instruction. We can have an instruction called move. What this instruction will do? This instruction will move the data from R2 to R1. So, here R1 will have the value of R2. Such kind of instructions are called data transfer instructions. We can have other control instructions. This is arithmetic instruction, this is data transfer instruction. We can have other branching instruction. What kind of branching instruction? Let us say I want to go to some location. So, we can have an instruction called branch to some location, let us say 16-bit hexadecimal number I am saying 4A10. This is a branch instruction specifying that this instruction opcode is a branch instruction and go to this particular location. So, branch to this particular location will move to this particular location, and whatever data is there in this particular location, it will be added with PC and it will calculate the current instruction that needs to be executed. Because branch to this location means in some particular location some instruction is present which we need to execute. So, this part of the instruction we call it an opcode, and this part is the operand. Now, see what can be an operand. Operand specifies either a single source or there can be two source and a destination of the operation. And source operand can be specified by an immediate data. I can just specify a number. So, that is an immediate data, or by naming a register. Just now I have shown how we can just give the name of the register, or specifying an memory address. Like specifying an memory address meaning we can have an instruction add R1 comma LOC A. So, in this we are specifying one operand a register, another operand a memory location. So, an operand can be a register, a memory location, or I can also have an instruction which I call add immediate, where I am adding with register 1 some immediate value, let us say 10. So, this kind of operand can also be specified, but this operand cannot be the destination operand. A destination operand should always be either a register or it can be, let us say, we can have another instruction that means content of location A and the content of R1 will be added and then the result will be stored back in LOCA. In LOCA, you will have content of LOCA and R1 will be added and it will be stored in LOCA. So, instruction consists of two parts, one can be operation, opcode, another will be operand, and what all operand can be present, I also discussed that. Number of operand varies from instruction to instruction, that also we have already discussed, that we can have a 0 address instruction, we can have a 1 address instruction, we can even have a 2 address or even have a 3 address instruction. So, number of operands that are present in an instruction that may vary. Also, specifying an operand, we need to know the various addressing modes. So, coming to what is addressing modes, we will be looking into in more details. Addressing modes actually is a way by which the location of the operand is specified in the instruction. So, there can be many possible addressing modes: immediate, direct, indirect, relative and index, and many more are possible. We will be seeing a few of them. Now, let us see this instruction format. If we have just the opcode, like let us take some example of NOP. NOP means no operation. No operation instruction specifies the processor that no operation will be taken care at this particular cycle. Halt. Halt the execution for this instruction halt will specify that halt the execution for some time. We can have one address instruction where only one address is specified along with the opcode. We can have two address instruction where we can specify two operand. We can have two address instruction where both can be memory location, add x comma y, overhead will be more. We can have another instruction where one can be register, another can be memory operation, or we can have another kind of instruction, a 3 address instruction where all are register. So, these are various instruction formats. Now, consider a 32-bit instruction example. So, we have a 32-bit instruction. So, suppose our instruction set architecture is having only 32-bit instruction. Fixed size instructions makes the decoding easier. Let us understand this statement. What do you mean by fixed size instruction makes the decoding easier? Let us say I am just giving a example. This is not corresponding to any real stuff. Let us say we have a instruction add and we have R1 and LOCA. So, this is an instruction and I have a 32-bit instruction, and this 32-bit instruction, some bits will be reserved for your opcode, some bits will be reserved for your register. So, this can be register destination, this can be register source, and this can be your memory location. If this is so, the total is 32 bit. And now we have to specify the bits in following. Let us say we have a total of 32 registers. If you have a total of 32 registers, how many bits will be required to specify a single register? 32 bit, so 2 to the power 5. So, the first register can be represented. So, 5 bits we will be requiring to represent a single register. So, this 0000 will be register 0, 00001 will be register 1, and so on, and the last register will be register 31. So, 5 bits will be required to specify one of the register. So, 5 bits will be required for this, 5 bits will be required for this. Let us say you can specify a memory location which is 20 bit. You can only have specify a 20 bit memory location. So, this will be 20. And then how many bits are remaining for the opcode then? 20 plus 10, 30. We have to frame or make our instruction within 32 bit. So, we have 2 bit left for opcode. So, if we have 2 bit left for opcode, we can have maximum of how many possibilities? 00, 01, 10 and 11. There can be 4 operation, operation 1, operation 2, operation 3 and operation 4. These 4 operation can be taken care by this, if we have this kind of format. I am just giving you as example, and this does not correspond to a real machine, but rather just to give you an idea that how the instruction format will looks like. So, coming here, fixed size instruction makes the decoding easier. This statement, easier how? Like you already know, coming to this diagram once more, you already know that first 2 bit is your operation opcode. So, you can only check this code to know, okay, this is the operation. You already know that these 2 is your register, and you already know that this 20 bit is your memory location. So, if you already know that all these bits are fixed, the total instruction 32 bit is fixed, and these bits are fixed for these. We can have various kinds of instruction, like here we have only one memory location. If we afford to have, we can have 2 memory location, we can also have that. But if you have such kind of this kind of mechanism where you already know well in advance, okay, these are fixed and this is how we have to do the decoding. So, the decoding task becomes much easier. So, the same thing that I have discussed, some instruction encoding examples are shown. Assume that there are 32 register. If we have 32 register, all of 32 bits, then how many bits are required to specify a register? 5 bits. If there are 64 registers, you will be requiring 6 bit and so on. Now, let us see some format. Let us say this is the format where you have these many bits for opcode 26, 27, 28, 29, 30 and 31, 6 bit for opcode, and these are for the register, 5 bit for register, and then you have a 16 bit immediate data. The 16 bit immediate data can be specified here. Let us take a sample example where we load R11 100 R2. What we are loading? We are loading the content from memory location pointed by 10 plus R2. So, first we have to add 10 plus R2 and then we have to put this 10 plus R2 in the MAR, activate the read control signal, get the value of it, and then what we do? We load it into R11. These are the following steps that will be required to execute this instruction. So, let us see where all it will be placed. This is the destination register R11. So, R11 will be placed here. So, R11 is 01011. Opcode for load will be loaded in first 6 bits. Then this is the source operand. One of the source operand is R2, it is loaded here, and 100 is the immediate value which is loaded here. So, this is how you can encode your this instruction into this binary form. Again, load can be having some value, let us say 000001 will be the load value. So, you can represent this using this particular format for this particular instruction. Let us move on. Now, if we have limited opcode facility, that means we can only have 64 operations that are possible with 6 bit. So, if you want to increase that, what can be done? What we can do here is that here this opcode will give you that what kind of function it will be taking care of, like it can be an ALU function, it can be a data transfer operation, it can be something else or other, and exact function will be specified by this 11 bit. So, let us see this. So, it is add R2, R5 and R8. So, the content of R8 and R5 will be added and will be stored in R2. Now, we see that we know that this is an ALU operation, this is the destination, that is R2, the source, there are two source, first source is R5 and the next source is R8, and this ALU function is an add function. So, we are encoding this particular instruction using this particular bits. Now, moving on to addressing modes. Now, see what we have understood till now, that we can see this that we have instruction, and we by seeing we are saying that okay, this is a register, this is a memory operation, memory location. But again you have to instruct the computer that see, this is a register, this is a memory location, then only your processor will do the required thing. It will go to the memory location, get the data. It will go to a particular register and get the data. So, what are addressing modes? Addressing modes are the ways by which the location of an operand is specified in an instruction. Let us move on. What is an addressing mode? So, as I said, they specify the mechanism by which the operand data can be loaded. So, it specifies that the location of an operand in the instruction, how the location of the operand is specified, whether it is a register, you have to get it from register, or you have to get it from memory location, etc. Some instruction set architectures are quite complex and supports many addressing modes, but instruction set architecture that are based on load store, they usually support very simple addressing modes. So, this is very important. If you want to have complex addressing modes, some of the instruction set architecture do have it, but this load store architecture basically they support very limited number of addressing modes. Now, what are the various addressing modes that exist? Immediate, direct, indirect, register, register indirect, indexed, stack, relative, auto increment, auto decrement, etc., based, etc. Now, see, I am telling you about so many addressing modes, but all computers, all architectures will not have all the addressing modes. This is the class of addressing modes that are existing in all the architectures, but different architectures have a set of addressing modes. So, we shall look into first some common addressing modes and how do they work. Coming to immediate addressing mode, here the operand is a part of the instruction itself. So, you need not have to go anywhere to get the operand, rather your operand is a part of your instruction. So, here no memory reference is required, no memory access is required to get the operand, and it is fast, but limited range, because you cannot specify, you can only specify a limited number using immediate mode, like add hash 25. When we write hash, that means it is an immediate data. So, when we write add hash 25, that means 25 will be added with accumulator, whatever value is in the accumulator, it will be added with that and it will be stored in accumulator. Similarly, so there is a mistake. So, this will be add I and this will be add. So, here this will be add, we are adding add R2. Okay, sorry, this is also an immediate data that we are adding. So, this immediate data will be added with R2 and the result will be stored in R1. So, we have an opcode is this and we have an immediate data. That immediate data is 42 here, which is added with content of R2 and getting stored in R1. Moving on with direct addressing mode, here the instruction contains a field that holds the memory address of the operand. So, in this direct addressing mode is that the field which specifies the memory address is your effective address. That means, this is the address from where you will get the operand. So, the operand here, let us say this is 20A6 is the location and content of 20A6 will be the exact operand that you are looking for. Like here add R1 comma 20A6, meaning whatever content is in 20A6 will be added with R1 and it will be stored back in R1. Now, here how many memory operation is required? As in the instruction you are specifying the address. So, you have to go to this particular address and fetch the instruction. So, going to this particular address will take one more memory access. So, a single memory access is required to access the operand. No additional calculation is required to determine the operand address and the limited address space. So, if this address space is 16-bit, so it is limited. So, we can only have direct addressing within that 16-bit span. So, this is pictorially we can show, this is the opcode, this is the operand address. So, this is in the memory. So, in the memory this operand is there, you go to that address, you get that operand. This is direct addressing. Let us move on, indirect addressing. The name itself suggests when it is indirect, that means in the instruction what it contains a field that holds the memory address, which in turn holds the memory address of the operand. So, let us see this with an example. Let us say we have an instruction add R1 comma LOC A. So, if you have written add R1 comma LOC A and this is your memory LOC A. LOC A contain another address LOC B, and now you will not get your operand from LOC A, rather you will get your operand from LOC B. So, you go to LOC B and your operand is here. So, it is indirect, it is not direct such that I go to location A and get the value like I got it in the previous case. In this particular case, you have to go to this location will give you another location, and you go to that particular location, that will give you the value. Okay. So, in this case, if you can see that you are requiring 2 memory access. So, 2 memory accesses are required to get the operand value. Slower, but can access large address space. Like in previous case, we can only access that 16 bit, but using indirect addressing, the address space can be little bit extended, and it is not limited to number of bits in the operand address, as I said, like direct addressing. So, here add R1 comma 20A6, where the content of this memory location will give you the operand. So, this is the operand address. First, this is a pointer as I explained, and then from there you go to another address which will give you the exact operand. Moving on with register addressing. So, register addressing is again straightforward. The operand is held in a register and the instruction specifies the register number. Very few number of bits are needed as the number of registers is limited, faster execution, but no memory access is required for getting the operand. So, register addressing means you are specifying in the instruction the registers and you go to that particular register, get the value. So, the value can be there, no memory access is required for this, you only go to this particular register, get the value and do the operation as required. So, modern load store architecture supports large number of registers. So, as I said, this is the register bank. So, register number is specified in the instruction and you go to that particular register to get the operand. Moving on with register indirect addressing mode. Here the instruction specifies a register and the register holds the memory address where the operand is stored. So, this is also a kind of indirect thing, where instead of a memory location, here I am putting that value in a register, putting the memory address in a register, and then we are, and this register holds what? It holds the memory address, but not the operand. You have to go to that memory address to access the operand, can access a large address space. So, one fewer memory access as compared to indirect addressing mode. So, in here how many memory addresses required? First you are hitting a register and then you are hitting this R5. Now, R5 contains some memory location. You have to go to that particular memory location and get the value, then you do accordingly. So, just see here, this register will give you a memory location and this memory location is fetched from the memory, the data from this memory location which is in the register is fetched from the memory and we get the data, the operand. So, this is register indirect. In the register we are putting an address and that address stores my operand. Moving on with relative addressing. Relative addressing is always with respect to PC. Why it is required? Let us see that the instruction, this kind of addressing modes, the instruction specifies an offset of displacement which is added to the program counter to get the effective address of the operand. Since the number of bits to specify the offset is limited, the range of relative addressing is also limited. So, if a 12-bit offset is specified, it can have values ranging from minus 2048 to plus 2048. Let us understand this. Relative addressing means with respect to PC. That means relative to PC how much you can go. So, for branch instruction, if you recall, what happens in branch instruction? In the branch instruction, we specify a branch address. So, when we specify a branch address, that means I have to go to that particular location. How will I go to that particular location? To go to that particular location, in the PC you have to load that particular address. How will you load that particular address? So, this is an offset that is given in the instruction, that is added or subtracted depending on where you are branching. You are branching above or you are branching below the address. That particular branch address will be added with the content of the PC, and then the PC will be loaded with a new address where you have to go for branching. So, in such kind of cases, we require relative addressing modes. So, here you have an opcode, this is the offset. The offset is added with the content of PC, and then where you go and you fetch the operand. So, your operand is residing by adding these two content, then you fetch, then you get the operand. Moving on with indexed addressing mode. Here in the previous case, we have seen in relative addressing modes, the content of PC is added with the offset value. Now, here either a special purpose register or a general purpose register is used as index register in this addressing modes. And where it is required? You consider an array. What is an array? Array is a consecutive memory location. So, if you load a particular address, you know the first address of an array, how will you go to the next address, we add plus with respect to how your memory is organized. Okay. You add that and you go to the next location, then you go to the next location, and so on. In a similar fashion, here in index addressing mode, it is somewhat required that you add that general purpose register value. It can be used for it can be used as index register, and this instruction specifies an offset of displacement which is added to the index register to get the effective address of the operand. So, let us see with this example, it will be more clear. Now, see 1050 in bracket R3, that means content of R3 will be added with 1050, and then that location will give me the operand. And where it can be used, as I said, let us first try to understand this once more. So, 1050 is added with R3, we get a value, that value is loaded, searched in memory, that particular address is searched in memory, and we get the operand. And it can be used to sequentially access the elements of an array. So, in the element of an array, we load the first address and then we move to the next address by adding an offset to it. So, offset gives the starting address of the array, and the index register value specifies the array element to be used. The first can be 0th element, then the next, and so on. So, here this index register, you get this added with this offset, this particular address is searched and we get the operand from there. Next come to stack addressing. In stack addressing, we already know the operand is implicitly on the top of the stack, and it is used in 0 address machines much earlier, where if I specify add, this automatically means that the first two element on the top of the top two elements of the stack will be taken out and will be added and will be stored back there. Push x will push the x value into top of the stack, pop x will take out the top value to this location. So, many processors have a special register which is called a stack pointer that keeps track of a top of the stack. There are some other addressing modes as well, like base addressing modes, base addressing mode. So, in base addressing mode, the processor has a special register called base register or segment register, and then what happens here is all operand addresses generated are added to the base register to get the final memory address. So, now we have a register with respect to base register, the processor generates the address. Let us say the processor generates the address from 0, 0, 1, 2, 3, and then you have stored some address in base register, let us say 1024. So, 1024 will be added with that particular address to go to the exact address. So, this is what base addressing means, and it allows easy movement of code and data in the memory. We can also have another addressing mode, auto increment and auto decrement addressing mode. It was first introduced in a PDP-11 computer, and PDP-11 was one of the most popular mini computers in the 1980s. So, auto increment and auto decrement, it means that if you load an address, load a register with some address, you can auto increment it, you can access that value, then you increment it, or auto decrement means you access the value, then you decrement it. So, either way you can implement this. So, auto increment, auto decrement we have also seen in C, like A plus plus and A minus minus, auto decrement and auto increment operators. So, in the similar way we can have such kind of addressing modes also. So, now we came to the end of lecture 7. So, what we have seen in this lecture is that addressing modes, which are very important, and the instruction format. We will move on with the next, in the next lecture we will be seeing now the types of architecture. Thank you.